All right, general chemistry class. This is the video for Monday, March 29. And here are the announcements, assignments. For the next stage in ALEKS, by the way, we're a little bit further ahead in class than we are for ALEKS. So we've already talked about buffer solutions, titrations. ALEKS chapter 8a is due this Thursday, and then ALEKS, the second half is due next week. Now, keep in mind that we have class today and Wednesday, and by then you should have absolutely everything you need to know to be done for ALEKS by April the 1st. And to be completely fair, by Wednesday, we're going to be done with all of chapter 18 and be moving on probably to chapter 19. I may end up moving up this due date to give you some extra time for OpenPy for ALEKS. So I'm guessing that I'll probably leave this to April 1st, and I may put this something like April 3rd or something like Saturday, just to make sure that we get this wrapped up. So keep in mind that that April 8 due date is a little bit loose. This week, we're doing Lab 7. We're going to be working with buffer solutions in lab. We're going to cover worksheet 18, and I'm not sure if that's posted or not yet, but if not, I'll make sure I get that up soon. And then just keeping it on our calendar, coming up in about 3 weeks, we have exam 3. A little despair to start our day today. Until you spread your wings, you have no idea how far you can walk. If you find yourself struggling with loneliness, you're not alone. And yet you are alone, so very alone. Ouch. If at first you don't succeed, failure may be your style. Money can't buy you love, but it can buy exotic cars and luxury yachts. Once you've got those covered, you'll be fighting love off with a stick. Because making it look good now is more important than providing adequate support later. One of my favorites. Madness does not always howl. Sometimes it's the quiet voice at the end of the day saying, hey, is there room in your head for one more? All right. Now, chapter 18, buffer solutions. Let's just do kind of a quick review of where we've been. So for weak acid, excuse me, let me pause. We've talked about what you do, how you calculate pH with strong acids in water. We've talked about how you calculate pH with strong bases in water. Strong acid in water, it's only the hydrogen ion concentration that controls the pH. For strong bases, it's hydroxide concentration that controls the pH. For weak acids in water, it's a weak acid equilibrium reaction described by Ka. For weak bases in water, it is simply a weak base reaction described by Kb. Remember that a weak acid can be a cation, neutral, or an anion. A weak base can be all of those things as well. It could be a cation, neutral, or an anion. If it's a weak acid, it is actually donating an H plus to something else. If it is a weak base, it is accepting an H plus from something else. So keeping in mind exactly what you have tells you how to work a problem related to it. And you have the tools, you know how to work through these. You just have to recognize what you've got. And once you know what the situation is, you can apply those principles to solve the problem. In this particular case, we have a weak acid titrated by a strong base sodium hydroxide. Notice this little hitch in the curve early on. To review, right here, we only have weak acid and water. If we're going to calculate the pH right here, HA plus water goes to A minus plus H3O. This, for acetic acid, this would be an example. This is your weak acid only. This is your weak base A minus only. At the equivalence point, all you have in water is the conjugate weak base plus H2O. This is a weak base problem. This is a weak acid problem. All the time. All the time. You know this is weak because, first of all, this pH is a little higher, and you see the hitch in the curve, and that tells you that's characteristic of weak. Not always, but usually. Now, in this area here, this is the buffer region, and you use the Henderson-Hasselbalch equation. When you reach this particular area, this is where you have excess hydroxide, and this is what controls the pH. Extra hydroxide, nothing to do with the weak acid or the conjugate weak base. So here are some of the exceptions to where you find that hitch in the curve, which we talked about before. Strong acid, strong base. You can pretty much tell right away, look how low the pH is. It won't always be this low necessarily. It depends on the concentration of the weak acid one starts with. But nevertheless, strong acid, this could also be a strong acid. But this is actually a weak acid with a very high Ka value, relatively speaking. As Ka drops, notice how the curve changes. So this is very typical for a weak acid strong base titration. This is typical for a weak acid strong base titration. Just to recognize that all weak acid titrations are not the same. And then here we have a weak base as opposed to a strong base. A strong base titration curve would be flat across the top and then straight down. With the weak base, we see a little bit of a hitch down, and then we also have, by the way, this is the buffer region right here, between here, just before equivalence, to just after the titration has started. That's the buffer region. Polyprotic acids and bases. An example is oxalic acid. Oxalate, which is C2O4 oxalate ion. If we have oxalic acid, this is Ka1. It is how the weak acid releases that first hydrogen ion, forming hydrogen oxalate. Weak acid, conjugate base. The Ka is available. I mean, these are listed in tables. However, hydrogen oxalate also has a hydrogen that it can give. And so the second hydrogen coming off looks like this, where hydrogen oxalate gives a hydrogen ion to water, forming hydronium ion and just plain oxalate. This is described by a second K value. This value will always be higher than this one. They're often separated by 10 to the third or more. Notice this is 10 to the minus second, this is 10 to the minus fifth. That's very normal for polyprotic acids. There's usually, not always, but usually some kind of a bigger gap, kind of a gap between those two values. And the reason for that is because this is pKa1 and pKa2. Here they're separated because these are two distinct hydrogens that we're pulling off. This would be dihydrogen oxalate, or let's call it H2A. This is H2A only. It's a weak acid problem. This is the buffer region between H2A and HA minus. Here, the pH is equal to the pKa at the very center of the buffer region. This is where the H2A concentration and the HA minus concentration are the same. Let me just mark this. Let's just mark exactly what we have in these different locations. And we're good. All right, so here we have H2A, the diprotic weak acid. Here, the concentration of H2A is equal to the concentration of HA minus, right here. Right here, the only thing we have in solution is HA minus. That's all, nothing else. This is where we start, This is where this is being converted into this. This point is where the two species are equal. And at this stage, we've added more and more hydroxide to strip this first hydrogen off until all of it becomes this. This is the first equivalence point. First equivalence point right here. Moles of hydroxide are equal to the moles of H2A. As we keep adding, we begin stripping this second hydrogen off. So at this point right here, the concentration right here, the concentration of this HA minus is equal to the concentration of A2 minus. This is the second buffer region. This is the second buffer region. So this is the first buffer region. This is the second buffer region. At the exact midpoint of the second buffer region, this is where the pH is equal to pKa2. Then we reach this point. The only thing in solution is this, A2 minus. That's all that we have. This is the second equivalence point. And then out here, excess OH, excess hydroxide output. We can calculate the pH at any point along here, but we are not going to do those calculations. I just want you to be able to recognize what you have at different locations on the titration. All right, I guess that's good enough. So for acid-base equilibria, for titrations, we can have a strong acid and strong base. We can have a weak acid with strong base. We can have a strong acid, weak base, or a weak acid, weak base. We are not touching this because that's beyond the scope of what we want to talk about in this course. All right, so here's the key for any acid-base problem. What are you trying to find? What is the question asking you? And then what information do you have to start with? What kind of a problem is it? Is it a weak base titrated by a strong base? A weak acid titrated by a strong base? Is it some kind of a mixture of things? Then once you know what you have, write a reaction. It's either a weak acid plus water or a weak base plus water, if it's weak acid or base. Then you enter concentrations. If you need to, you use the equilibrium constant expressions, or the Henderson-Hasselbalch if it's a buffer. Let's take a look at these. Here we have a series of questions. Let's see if we can, let's see how we would approach this. Okay. We have 50 milliliters of 0.1 molar. So this is, let's just take the first one. 50 mils. We want to determine the pH, by the way. So we have 50 mils of 0.1 molar HNO3, strong acid. So we know that we have hydrogen ion. Then we have 50 milliliters of another concentration of KOH, which is hydroxide. So now we know we have hydrogen ion and hydroxide. And we're starting with both of them. This comes from a strong acid, this comes from a strong base. I'm only looking at this first line for now. So what are we trying to find? pH. What are we given to work with? Amounts of this. We have some hydrogen ion, we have hydroxide. Sizable amounts. So what do we know? We know that if these two are together in solution, they are forming water, according to KW. They are going to use each other up until one of them's gone. How do we determine this? Volume times molarity gives us millimoles. 50 times 0.1 is 5.0. 5.00 millimoles of hydrogen ion is what we're starting with. How much hydroxide? 50 times 0.05. This is 2.50 millimoles. When we put these two together in solution at the same time, they use each other up until one of them's gone. So we're left with all of the hydroxide being used up, and we have an excess of 2.50 millimoles of hydrogen. This is just like a strong acid, strong base titration calculation. So in order to calculate the pH, we have 2.50 millimoles of H plus in what volume of solution? What's the total volume of solution? Well, we have 50 mils of the acid combined with 50 mils of the base. 50 and 50 is 100 milliliters of solution. Now all we have to do is calculate the pH. So you can try this at home. 2.50 divided by 100, 0.025, and we want to do the negative log of that, 1.602. We'll call it 1.60. That's it. That's the first one. Any questions? Beautiful. Okay. Let's look at the second scenario. We have, instead of HNO3, we have HNO2. Changes the whole problem. Changes the whole problem automatically. Because this is now a weak acid, and this is now its conjugate base. It's KNO2. So let's write down what we have. We have 50 milliliters of 0.1 molar HNO2. How many millimoles? 50 times 0.1 is we have 5 point, we have HNO2, 5.00 millimoles. And on the other side, we have 50 times 0.1, that's 5 millimoles of KNO2. This is nitrite. KNO2, is it soluble in water? Of course it is. You know this because all potassium salts are soluble. So in other words, this is the molarity of potassium, this is the molarity of nitrite. We have a weak acid and its conjugate base in solution at the same time. So how do we find the pH of this particular problem? Well, by now you should recognize this is a buffer. We have a weak acid conjugate base combination. pH is equal to pKa plus log of NO2 minus all over HNO2. The weak base over the weak acid, the conjugate base over conjugate acid. These two are the same number. This is 5 and this is 5. That cancels out. So the pH of this solution is simply negative log of the Ka of nitrous acid. So it is the Ka of nitrous acid. Nitrous acid. Okay, of course, I'm trying to find the Ka of nitrous acid. and I'm not finding it right off the bat. So here's what you do. You go and look up the Ka for each NO2. It's probably in your book. It's probably, well, I know it's in the, I know it's in the chapter 16, 17, or 18. Look it up. There's a table in the back of the book. Find it. Take the negative log, and that's the pH. That's all you do for the second one. Let's take a look at the third scenario. We have 50 mils of 0.1 molar ammonium nitrate. Ammonium nitrate. Is it soluble? Yes, it is. All nitrates are soluble, and all ammonium salts are soluble. So this is very soluble. And we have 50 mils of 0.1 molar ammonia. So what do we have? We have NH4, NH3, together in solution. We have 5 millimoles of each. We have a buffer solution. We have a buffer solution. So the pH is equal to the pKa plus log of NH3 all over NH4 plus. NH4 conjugate base over conjugate acid. It is always the conjugate acid base pair here, base over acid. So this is just the Ka for NH4 plus. We know that the Kb for ammonia is 1.8 times 10 to the minus fifth for NH3. And then, so therefore the Ka for NH4 plus is equal to Kw over Kb. That is the Ka for ammonium ion. You take that number, take the negative log of it, that is the pH of the solution for the third scenario here. It's knowing what you're given, what you start with, knowing what you have to start with, and knowing and then finding what you're asking for. All right, let's look at the last one. 50 mils of 0.1 molar NH3. We have 50 milliliters of 0.1 molar NH3. That's 5 millimoles. We have 50 milliliters of 0.05 molar HNO2. 50 times 0.05 is 2.5. Of HNO3. This is a strong acid, so polarity times volume gives us millimoles of H plus. Strong acid. This is so critical. It is so critical that you know your strong acids and your weak acids. Given this, what happens? NH3 I can write it this way. If I start with 5 millimoles of this, and if I add 2.5 millimoles of this, this is how you would do a weak base strong acid titration. It's just like how we do a weak acid strong base titration, except it's a little bit different now because we're looking at hydrogen being added to a weak base. Adding H plus. How does H plus affect this equilibrium? If we add hydrogen ion, it is going to force this equilibrium in a given direction. If we add hydrogen ion, we can think of this two ways. Adding for every millimole of NH3 we have, for every millimole of H plus we add, it forces a hydrogen onto ammonia, converting it into NH4 plus. Here's another way to look at it. For every millimole of H plus that we add, it pulls an OH out of solution, driving it, forcing this reaction to the right. So we know that this reaction is going to the right by 2.50 millimoles. Because adding this hydrogen ion is forcing that hydrogen ion onto that many millimoles of ammonia. So this is not an equilibrium. It's forcing it to the right by adding hydrogen ion. We're left with 2.50 millimoles of ammonia, and we have just formed 2.50 millimoles of ammonium ion. What happens to hydroxide? That is changing. That is a variable now because we just pulled a bunch of this out by adding the H plus. So now what we have is a buffer solution. So because we have a buffer solution, I'm just going to rewrite this. So that it looks like an acid-base reaction. And the reason I'm rewriting this, all we have to do is know that we have 2.5 millimoles of ammonia, 2.5 millimoles of NH4 plus. I wrote it this way because this is how Henderson-Hasselbalch is written. So pH is equal to pKa plus log of NH3 all over NH4 plus. It's just like what we had in this scenario here. We had equal numbers of millimoles of ammonium ion and ammonia. We actually have the exact same problem. We know the pKa, this is 2.50, and this is 2.50. That divides out. So the pH is simply equal to the pKa of ammonium ion. In other words, we will get the exact same value for these last two. We approached them, we arrived at the same process in two different ways, but we end up with the same value because the pH of the solution is equal to the pKa of ammonium ion. All right, we are done with acids and bases. Done with acids and bases. As far as talking about them, of course, there will be the minor thing of Alex and an exam coming up, but hey, you're good now. And I forgot a U. Boy, I apologize for that. That's what happens when I type fast and ignore it. Chapter 18, solubility equilibria. This is the last part of 18. So we've been talking about acids and bases for 2.5 chapters now. Almost feels like forever. What is an acid? What is a base? How do they react in water? What happens when we mix and match, when we combine? The nice thing about acids and bases is that all the coefficients are always 1. So you have your Ka expression and your Kb expression. You have your Ka for a weak acid, your Kb for a weak base. If you're going to have a buffer, it's convenient to write the weak acid reaction because the Henderson-Hasselbalch easily can be seen in that particular aspect. I'm going to change this because I hate leaving things. There we go. All right, solubility equilibria. Now we have our U back. Let's do a quick review of ion solubility, or solubility of ionic salts. We already did this in this earlier in this semester, so we're going to do it again. These anions are always soluble. Always, always, no exception. These cations are always soluble. Always, always, no exceptions. These three anions are usually soluble. Remember that these are the exceptions: silver, lead 2, and mercury 1. They are the exceptions for solubility, but these guys are almost always soluble. So when you see them in a salt, chloride, bromide, iodide, you assume soluble, but is it one of these guys? Solubility rule 4, sulfates are generally soluble, except for these. The first three are the same as we have for chloride, bromide, iodide, but now we add in 3 of the alkaline earth metals cations. 3 of the alkaline earth metal cations, calcium, strontium, barium. These will precipitate with sulfur. So to this point, we're talking about salts that are generally soluble. And then for rule 5, when you see these anions in a compound, the first thing you should think of is insoluble, unless they're paired up with one of the cations from rule 2. Hydroxides are generally insoluble, unless it's one of these guys. Carbonates are generally insoluble, unless it's one of these guys. So let's go through a few quickly. Soluble. Soluble or insoluble? Soluble. Soluble or insoluble? Sulfates are generally soluble. This is soluble. Soluble or insoluble? Phosphates. Phosphates are generally insoluble, but lithium salts are always soluble. By the way, can you name these as we go through? Good practice. Soluble or insoluble? Nickel acetate. Acetates are always soluble. Nitrates are always soluble, even silver nitrate. Bromides are soluble. Lead 2 is an exception. Lead 2 bromide, insoluble. Hydroxides are generally insoluble. This compound is insoluble. FeI2. Iodides are generally soluble. This is soluble. Iron 2 is not one of the exceptions. Barium sulfate. Sulfates are generally soluble, but barium is an exception. Barium sulfate is insoluble. Potassium salts are always soluble. And of course, you know this as potassium chromate. This is mercury 1. This is mercury 1 because it's Hg2, 2+. You know it's 2+ because there are 2 - 1 nitrates attached. Soluble or insoluble? All nitrates are soluble. Soluble or insoluble? Sulfates are generally soluble. Copper 2 sulfate is soluble. Soluble or insoluble? Iodides are generally soluble. This is mercury 1. This is an exception. Mercury 1 iodide, for which this is the formula, is insoluble. All ammonium salts are soluble. Ammonium sulfide, even though sulfides are usually insoluble, ammonium sulfide is soluble. How about this one? Name it first. Do it. Iron 3 perchlorate. Chlorates are always soluble. Doesn't matter what it is. Okay, so there's a quick run-through exercise. What we're going to do is set up solubility equilibria. On Wednesday, we're going to go through all of the calculations that we need related to this. So here's how solubility equilibria works. Set aside acid-base. Now we're talking about solubility equilibria. Remember the 3 major kinds of reactions: acid-base, precipitation, and redox. We spent a lot of time talking about acid-base, and now we're talking about precipitation reactions or solubility reactions. And next we will talk about redox. But for now, this is where we're at with precipitation reactions, or the reverse precipitation, solubility. If you put a salt in water, does it dissolve or does it not? So remember, from the solubility rules, if a salt dissolves, it totally separates into its ions. If a salt dissolves, a solid salt dissolves, that is a cation anion from your cation anion sheet, it totally separates. Acids, all acids are soluble. It's not a question of if they dissolve or not. All acids dissolve. So for acids, the question is, are they strong or weak? In the case of salts, is it soluble or insoluble? So if we have an equilibrium set up, the equilibrium gets set up because of a tiny amount of stuff that will dissolve, usually a tiny amount. So we have to backtrack just a little bit, or maybe just qualify what we've been saying. So the simplistic overview of saying a salt is either soluble or insoluble by the solubility rules, the exercise we just walked through. For things that are insoluble, this is the equilibrium that occurs. We call them insoluble because for all practical purposes, they are. If we take silver chloride, silver 1 chloride, and we throw it in water, it is going to sit there as a white solid suspended in water. But a tiny amount of it, a very tiny amount of it, will give us a tiny bit of silver ion, a tiny bit of chloride ion. This is the equilibrium that gets established. K values for these things are small. They're much less than 1. These equilibria lie far to the left. These equilibria are always written salt on the left, cation and anion on the right. These are the only 3 components to any solubility equilibrium. We have the salt, cation, and anion. That's it. In the case of copper carbonate, copper 1 carbonate, copper 2, copper 1 carbonate. Remember your naming. We form 2 copper 1s and a CO3 2 minus. So you know the carbonate's CO3 2 minus, so therefore it takes 2 copper 1s to counterbalance that. Notice the difference from acid-base equilibria. In acid-base equilibria, all of our coefficients were always 1. For solubility equilibria, well, they can be 1, but they're not necessarily 1. So now we have coefficients that are not 1 possible. Look at this one. For zinc phosphate, we have 3 zincs and 2 phosphates. This is how you would write the equilibrium reaction for a insoluble solid. Now maybe we should switch to the term sparingly soluble. They're not totally insoluble, but they're sparingly soluble. KSP. Let's talk about KSP now. K is the equilibrium constant. SP stands for solubility product. SP stands for solubility product. I'm not sure that this is correct down here. I'm not sure that these numbers are correct. I'll need to check that out. Anyway, so don't take that last line as being absolute. So here we write the equilibrium constant expressions. How do we write their KSP expressions? All right. It's easy. This is called, by the way, K for solubility product, KSP. The solubility product is simply the product of the solubilities of the ions that are produced. That's where that comes from. So KSP for the first one is equal to concentration of Ag times the concentration of Cl minus. That's it. Those are aqueous. Excuse me. Should we be dividing it by AgCl? That's a solid. Remember that solids and liquids never appear in an equilibrium constant expression. So This is it. For this one, copper 1 plus, but there are 2 of them, so that's squared, times CO3, 2 minus. This is the equilibrium constant expression, the KSP expression, the solubility product expression for copper 1 carbonate. And then for this one, KSP is equal to zinc concentration to the 3rd power times phosphate concentration to the 2nd power. Now, the coefficients become exponents. The coefficients become exponents. And this is how you write the equilibrium constant expressions. Bring back some good memories from chapter, what was it, 14? Well, I hope so, because equilibrium's wonderful stuff. So this is what they look like. So these are the equilibrium constant expressions. All right, a couple of terms. And then we're going to stop in just a few minutes, and we'll go just a little bit further, but we're not going to go too far into the calculations today. So a couple of terms. Molar solubility. The molar solubility is the molarity of the salt that dissolves. We'll give you an example of that in a moment. The solubility product is the KSP. Sometimes the solubility product is sometimes considered the value of the KSP, but the solubility product is the equilibrium constant expression that comes out of all that. So let's just do it with this. We'll do one example of problem, and then we'll stop for today. Lead iodide in water. We already know that PbI2 is insoluble. I believe this was one of the insoluble compounds in that list that we just ran through earlier. So if we throw lead 2 iodide, PbI2, in water, it should be basically insoluble. But a tiny amount goes to ions, a tiny amount. So what is the molar solubility in water? That's the question. This is the problem. It's the simple question, what is the molar solubility of PbI2 in water? The first thing that we do, write the reaction. Write the reaction, and then complete an ice table, and then solve for X. So here's the key about molar solubility I told you I was going to come back to. Molar solubility is the molarity of the compound that dissolves. It will always be X in the ice table. Molar solubility is X. Excuse me. Here's the reaction. Here's the reaction. Let's complete the ice table. We start with PbI2. We have none of this. We don't put this in the equilibrium constant expression because it's a solid. We know that the KSP expression is going to look like this because of our reaction. Coefficient of Pb2 plus is 1, the coefficient of I minus is 2. So our equilibrium constant expression looks like this. Our ice table, we form X lead and 2X iodide. Remember that, and this is different from acid-base equilibrium now. We can have values greater than 1 here. It is not just plus X, we can also have plus 2X. At equilibrium, we have X and we have 2X. In other words, the iodide is formed in twice the amount that the lead is. The molar solubility is X. The molarity of the lead iodide that went to the right is X. Molar solubility is always X. Now what we do is we take these and we plug them into our equilibrium constant expression. And we solve for X. So we have to look up the KSP. The KSP is 1.4 times 10 to the minus 8. So if you don't happen to have that memorized, it will either be given to you or you can look it up in a table. We are still, remember, we're trying to find the molar solubility of lead iodide in water. So the molar solubility of lead 2 plus is X. The molar solubility, let me back up. The equilibrium concentration of lead 2. The equilibrium concentration of lead 2 is X from the previous slide. The equilibrium concentration of iodide is 2X. Not just X, but 2X. So when we put them into the equilibrium constant expression, this whole square bracket thing is X. This square bracket thing is 2X. That whole 2X thing gets squared. It is not just the X that gets squared, it's the whole thing 2X that gets squared. So this becomes X times 4X squared, which is 4X cubed. Now all we do is divide by 4, take the cubed root, and we solve for X, which is 0.00383. Once we know X, once we have solved for X, that is the molar solubility. That is the molarity of PbI2 that dissolved in water. How are you doing with that? Okay? All right, we're going to stop here for today. Solubility product, PbI2 in water. We're going to come back and finish up everything you wanted to know about solubility product and molar solubility and sparingly soluble salts on Wednesday. So we have something to look forward to.